Morning, everyone. Thank you for coming, and I understand for some of us it's a very early morning, and so I appreciate it, and I hope I don't bore you to death. So what I'm going to talk about is work that I have done mostly in Canada, in Newfoundland. I'll show you more or less in which region. And it was about the development and deployment of an unmanned Iceberg observation system with targeting offshore problems that are well, pretty prominent in Newfoundland. So I hope I leave some time for questions afterwards, but please feel free to talk to me during or after. So quick and outlined, I give you a motivation with a system description, concept of mode and modes of operation, some of the trials we've conducted, and some of the results. I will only show you the nice results, of course. We can talk otherwise over beer, over the other results. And also just a very brief glimpse of what we are, the research group we are establishing right now at Marum, what we are going to develop, what we're working on. I'm at Marum, I should say, or the University of Bremen since 2017, July 2017, so I'm pretty new there. I'm pretty excited about that. And it has been a nice welcome to the community here in Europe to work with you. So let's start. Problem description. It's a large problem. You have, this is Greenland, this is Labrador, the US, here's Nova Scotia, Newfoundland, the US starts down here, the rest here is Canada, and the Arctic starts further up there. We have an eastern Greenland current that comes down, travels up the west coast of Greenland again. That's where all the glaciers are that are calving on the western side. And if you have followed the climate people, there's in Disco Fjord, I think it's up there, there's the fastest calving fjord right now where the glaciers are calving very quickly. So climate change makes it actually more dangerous in terms of iceberg occurrences because they're calving much quicker. They get carried up north, first of all, and then, I mean, this is basically only the highway. There's a lot of side roads going, and then ultimately they come over to the Canadian side and travel down with the Labrador current along the Labrador coast here towards Newfoundland. This is a map I got from Scientific American. So the Titanic sank about here. The iceberg that sank at the Titanic was supposed to come also from those glaciers up there. I don't know how they determined it, but that's what people say. So let's stick to that for a second. The offshore installations are on the Grand Banks here. Right now they're in shallow water. They're in about 100 meters of water, more or less. There are some developments in the Orphan Basin that are going to go ultra deep to 2,500 meters, which will be more or less subsea installations. Since the icebergs get carried down here, this part is also called Iceberg Alley. They occur usually during May, June periods. They can start a little bit earlier, they can go a little bit longer depending on when the melts occur, what the sea ice is doing. But nevertheless, there's a big threat here to the platforms. The Gulf Stream comes up here, so the water gets quickly warmer here, so they decay. But do they decay fast enough? Are they a threat or not? So they have the offshore operators, there's 3 gravity-based structures that basically stand on the seafloor, and there's 2 FPSOs, they're basically floating production storage units that are large ships that are more or less permanently anchored on site, but they could theoretically detach and move to the side if an iceberg gets too close. The same thing should be true for the gravity-based structures. Nobody has done it, but they're supposed to be designed that way. Otherwise, they're looking into circles around these platforms for doing actions when icebergs approach them. So there's a whole management plan going around it. I can use this. So the approaches, as I said, there's the International Ice Patrol that flying, to disregard the map for a second, that's a completely different area. I come to that. There's a reason for that map. Don't get me wrong here. Just stick to me here. There's the International Ice Patrol that flies patrols, and they do visual and radar recognition if there's icebergs coming down, and then that gets posted into a map every day, if possible, and they will basically, people look, do we have an occurrence of icebergs in a certain quadrant, and then they act on that. There's iceberg management. Iceberg management is one side detecting, the other side is actually doing something about it if you can. A water cannon, the offshore supply vessels that are always on watch around the platforms, they have high power water cannons on it, so they basically shoot at the icebergs and try to push them away if they're of the size that they actually can do it. And pushing is a little bit hard to say, it's more nudging a little bit. The other thing that happens is iceberg towing. You basically lay a net around an iceberg, and you have one or multiple offshore supply vessels that try to pull it a little bit away. And that's where the map comes in. So this is a hurricane map. Here's Cuba, Florida. If you look at the hurricanes, you have a position of a hurricane. Just think of it, that's a position of an iceberg. And they're trying to predict, where the hurricane is actually going. So they have been becoming very good in that. Because they have a lot of atmospheric information. There's quite a bit of oceanographic information about the site, so they can do that. The same thing we would like to have for an iceberg. The detection is hard, but how an iceberg drifts is influenced much more by the ocean and by the atmosphere, by the wind, waves, and currents, plus the deterioration, if you know better, how the water changes in terms of temperature, so the iceberg decay is very important. And if you can nudge the iceberg here in the beginning of this track, you might get out of the range of your offshore installation. So the earlier you detect it, you can actually do something about it if you predict it right where it goes. You don't want to nudge it, and then it goes to where you don't want it to be, right? So that's an important kind of fact. So what you want to have is a more accurate iceberg position information and also iceberg decay prediction. It means, how does an iceberg change? We don't have the luxury of having a ship staying with icebergs, not a single one, but for long periods of time, to look how it changes over time. It's very costly undertaking. The weather conditions are not always favorable for ship surveys and sticking with that. A ship costs about $50,000 US a day. And if you want to go in an iceberg that takes weeks, you can actually sum it up how much that will cost you to do that, right? And why do you want to do that? You want to have more effective management, lower risk, and ultimately lower cost. Lower cost, not necessarily in dollars, but also in human resources, endangering people. Because the North Atlantic, the West Atlantic is particularly harsh, cold, and there's also a lot of fog, which makes it very difficult actually to do optical systems, for example, to detect icebergs. Radar is the preferred way of doing it. So here, the problem is that these more accurate predictions of iceberg drift and decay are because of locally inaccurate numerical oceanographic models, and iceberg shape information is not available, so that makes it very hard to do. If you look at the numerical models, they have grid cells of 1.5 kilometers. In coastal areas, you can get much, much smaller. So in order to get the resolution to predict something like that is very, very hard. So the objective we were basically driven by is better modeling needs more accurate data. So that's collaboration with oceanographers. And what we wanted to do is provide a long-term monitoring and observation solution for improved iceberg modeling and prediction capabilities, in particular drift and decay. For that, we wanted to collect high-resolution iceberg drift data, provide data of iceberg shape and size above and below the water, detect changes in the state of the iceberg, and provide meteorological and oceanographic data in the vicinity of the iceberg. That's what we usually refer to as met-ocean data. So you get above and below water, basically the weather, if you call that. So here was the concept. It's a little bit, I've seen better concept drawings, and I see that some of the fonts have shifted again, but that's okay. So the concept was to have a platform in the water. This is already stepping a little bit ahead. This is a spar-type platform I talk a little bit more about. have an underwater vehicle. In our case, we talked about gliders, possibly a drone, and a beacon on the iceberg that gives you the location. Beacons already exist, however, they fall off very easily. They drop them off airplanes, they lie on the iceberg, and if they get washed over or if the terrain is not flat, they wash away. We looked into anchoring of beacons. I think it can be done, but it's not a trivial task. So we didn't address, we built a beacon, we had the drone, but we didn't do the whole anchoring business on the iceberg. We were focusing, and this talk is focusing on these two components here. The surface vehicle, or semi-submersible if you want to call it, and underwater glider and how they do. So locally we want to do coordination, collaboration of the assets, do some sensor fusion, and increase the platform autonomy, because we don't have the luxury of having a ship with it, because then we would be back to square one. Why don't you do it with a ship in the first place, right? Onshore would be then the data products. For us, it was very new as an academic. What does industry really want to see? We provided them with a nice point cloud the first time we got results, and we were very excited about it. And then I said, what is this, right? And so they needed a nice rendering where you lose a lot of the information that's in the point cloud, but that's kind of what they were dealing with. And that's what they were interested in. And they were very happy with that. So that's what we're doing. And I think I move a little bit too slow. The technological challenges are quite nice, to say the least. We have a problem of endurance. We want to stick around icebergs for long periods of time. We want to have diverse capabilities, multimodal. Peter, you're here, I think, yeah. Onboard data processing to some extent, because we have in the final product, we were thinking of having a satellite link where you cannot have an unlimited data link, so you have to process data on board and send only information. You can request more later, but that was kind of a thing. The platform autonomy, sensing, we already knew we don't have enough money to start with, and the capabilities of buying and building for each single thing an own sensor. So we were looking into sensors that have multiple uses, and I just picked one. This is a K-band radar that we developed. Initially was thought just to use it for collision detection with icebergs above water. It turned out that the K-band is really good to detect also the sea state. So we had a whole project. Actually, there's 3 or 4 papers came out of that on wave state detection from a short-range radar, 200 meters and shorter, where you can detect basically the bragg scatter on the surface, and from that, with a wave model, you can actually then derive the sea state. And this one, we were very ambitious because it's clear up there. It had coupled with a rotating sonar also a camera that looks in the same direction, so you could do sensor fusion. We never got to that part. We took pictures, but we never fused it because it worked very nicely for us. So that's what we did there. This is just brief, and I'm not going into any details. That's a beacon, a small satellite beacon that you can drop from a drone with no anchoring device. It gives you GPS and orientation, because we also wanted to know not only how the iceberg moves, also how it actually rotates. That's nice information if you do iceberg mapping and shape information. The drone was used a couple of times for aerial imagery. Oops. For aerial imagery, and for the beacon deployment, we had the concept, but we never actually dropped it. So now to the main part of the system. We have a surface and underwater vehicle. For the surface vehicle, we decided relatively early on a spar type vehicle. The reason for the spar type vehicle is, if you're familiar with ocean engineering and naval architecture, it's basically like a buoy. So we wanted to operate in high sea states, up to sea state 6, we wanted to survive, and sea state 4, we wanted to operate. We don't have humans on board, so we don't need space to put somebody in, and we didn't want to move a lot. The concept to get the endurance that we need was we stick to the iceberg, we drift with the iceberg most of the time, and only occasionally we adjust our position to stay in close range or do a survey when we occur. So we don't want to continuously propel the vehicle. So that was our concept in order to reduce the power. And so for that, we developed this test bed. It's about 7 meters high, 900 kilograms. Like all of us, we gain a little bit of weight at the end of the day. And the task was, first of all, a technology test bed. We wanted to merge all the different technologies, a communication hub at the ocean-atmosphere interface. It turns out a lot of oceanographers and atmospheric scientists are actually interested in these upper 10 centimeters of the ocean, which this would also provide a very nice platform. We got actually more requests for doing atmosphere-ocean interaction than for Iceberg work. And also as a mothership for an underwater vehicle. For the underwater vehicle, because I've been working on underwater gliders for the last 16 years, and we developed the hybrid glider. We wanted to use the hybrid glider because of endurance. We didn't want to use a small AUV and launch it from the mothership. We wanted to have a glider that's mostly doing oceanographic work, but we can retask it to do an iceberg survey. So here's just the scale, and there's a little person drawn to it. And like an iceberg, most of this vehicle is actually underwater. We have the 2 bulbs underwater. One is basically battery storage in the deep part, and the other one has computational and other components in it. Above water, we have LiDAR. And before I explain that to you in this slide, I show it in this slide. The waterline is roughly here. So we have this radar I told you about on it. We have also a commercial long-range radar on it, satellite communication, some beacons, a weather station for the atmospheric conditions, cameras. We use the Velodyne LiDAR on it. Below water, the main sensor was the multi-beam sonar. Somebody wrote here side-scan sonar. That's not true. That's a blue view multi-beam. Altimeter, an ADCP for current measurements, a USBL system that we could use to communicate with the glider. The components we developed more or less from scratch were these 2, besides the whole vehicle, I should say. A magnetically coupled and geared thruster. So it's not only a coupling, it's also a gear, so we don't have a mechanical gearbox on it, and the radar. The propulsion system on the vehicle, I should say that, you see here there's a part to the left and a part to the right. So we have differential thrust to steer it. There's no rudder on it, on this vehicle, right? And I'll show you something what has to do with it. So from a naval architecture point of view, you place it in a location where you have your point of pressure, so the vehicle drives nicely upright through the water, and you can do all the measurements you want, in theory. Here is basically the internal structure. I'm not going to bore you with it, but it's more or less a CAN-based system. And for the high data rate sensors, we have Ethernet. And we have power over Ethernet applied to the whole system where we can turn sensors on and off as we need them. CAN bus was selected because of availability, robustness issues, and we had a prior development for a smaller test bed where we had already seen the benefits of it, and we leveraged from that. So this is what the vehicle looks like in the water when it's not moving. At that point, that was in 2015, 2016. Here is a Holyrood. That's a marine base close to St. John's, about 20 minutes away. It's a very nice testing place. Most of the time very protected. And they were very helpful. The Marine Institute, you might have heard of it. Their Marine Institute is a part of Memorial University. This is Marine Institute of Canada, not there's another very famous Marine Institute in Ireland, and I think Gerard is going to talk later a little bit. And here in front of icebergs, what you see hanging off there was basically rigging when we launch and recover the system. How am I doing with time? Okay. So this was the first mission. We drew. Here is a small dock in Twitting Gate. Twitting Gate is a very popular tourist spot if you want to observe icebergs. People go there in May, and sometimes even July. Up to July, you have icebergs all around there, and there's iceberg tours, and it's a great spot if you're looking for icebergs. What we did there was we launched here. You see a little bit of. We drove around here for a while. And then the vehicle transited to an iceberg that was grounded up here and did about 7 circles around it, and then we drove it back. What I was alluding to earlier with the placement of the thrusters is basically in these 2 plots. The one plot shows your roll, the other one, the green one, pitch, and you see actually this pitch of 10 degrees when you're driving. So the vehicle was basically diving into the water until it equilibrates with the forces, and you kind of look down in the water with your sensors. And that has to do is you never get this pressure point right, because the sea states change, everything changes, so you will always have fluctuations. And with these bodies underwater, they act basically as dive planes to some extent. So they pull you down in the water until all the forces balance out again, and you keep on driving. So it's not sinking by any means, and the sensors were above water, but you had this one. For that reason, we installed a 3rd thruster below it, so we can actually modulate it and keep the vehicle driving upright. It turned actually out that the whole thing was actually more power efficient with the 3 thrusters than with the 2, because of the drag you had when you drive like this through the water. So it ended up pretty nice. And down here is just the heading changes, so the turns we did. The next slide, I don't know if that's going to play. Oh yeah, it plays. So this is Arvest. I should have said we have ROS running on the vehicle. And so we package all the data and we replay it on shore. So the data you see here is actually multi-beam data as a vehicle. Here's the vehicle with its frames moving along. This is around an island. This is not an iceberg, right? And so it drives around, and in a second you will see actually much higher density point clouds popping up. That's actually from the LiDAR then because we have the same reference frames. We can actually nicely show that. And now you saw how the LiDAR actually pops up very nicely above water, and the vehicle drives itself around the island and closes the loop. Then the LiDAR loses it again because it's not a very pronounced island because of the limited range. I guess if you would have a different LiDAR, you could do actually much better than that. The other thing you should notice is back here, this blue. That's some of the things that LiDAR picks up off the sea surface. You know, when you drive through, you get some things. Here. So just recall what I told you earlier about the initial concept. We wanted to have a system that can cooperate with an underwater glider. Here's the glider. So we had actually also the USBL on it, and on the glider we also installed a scanning sonar. Here's this part of the talk. I'm going to talk mostly about the glider work, and there's a reason why the glider looks a little bit strange to you, and that's the reason here. We integrated into a glider a scanning sonar. It's a Micron, a Tritech scanning sonar in the front that's tilted to the side. So you see here the top view. So it's tilted this way, so it scans basically a disk. You have to think about it. You can scan a disk around the glider. So on one side it looks forward, on the other side it looks backwards. So that meant we only can fly clockwise around the iceberg to scan it, actually. We tested the cone here, if it influences the sonar measurements, and there was only minimal kind of impact on that. So it worked very well. The thruster on it is, it's cut off a little bit here. It's a folding prop design. You can buy it now with a hybrid glider anyway. We initially developed it, and this one was just a further development. It was basically an outrunner motor in this case with a folding prop, which allows you to then to do not only the typical sawtooth profiles you see from gliders, but you can use it almost like an AUV, do horizontal flight. However, you have a problem with navigation because the navigation system on a glider is not that great, hence the USBL to help it actually with navigating. But for our task, we wanted to navigate not in an absolute sense, we wanted to navigate relative to the iceberg. So we wanted to stay relatively close to the iceberg to do the mapping, but we wanted to also stay far away from the iceberg, not to collide with the iceberg. The gliders move relatively slow, so I don't think it would be an issue of the collision impact. It would be more of a problem of getting hooked up into something, and you will be stuck with the iceberg until something else happens. Right? So for that, we implemented on the glider itself. So it's not something we did in post-processing. I mean, the development was in that row. We also implemented occupancy grid map, inverse sonar model to process the sonar data in real time on the glider, and then we basically conducted line of sight path following here. Why do you want to use a glider? Just a quick look. When you saw the multi-beam map, it looked actually pretty nice, and that's not what you get from a scanning sonar. But here's the problem: when you do a survey with a boat around an slide here. When you do a survey with a multi-beam sonar, you have to go deep in order to get the deeper parts of the iceberg. So the deeper you go, the less favorable your angles get. So you don't get a lot of energy return from your iceberg surface, which is a hard surface anyway to impact with this kind of thing. It's very smooth. It's very stealth in that sense. So the idea is to drive around the iceberg that's free drifting and rotating and close the loop, and from that detect actually the drift rate, but also the rotational rate through loop closure using point cloud processing. So this was from the ship, not from the glider, where we tried it out. We couldn't go too often around the other side because it was not deep enough. And so we drove around, got that. For a grounded iceberg, you have the additional difficulty that the iceberg is sitting on the seafloor. What's the difference between seafloor and iceberg? That's not clear. So for us, we said we're looking into free drifting icebergs, so we don't have a seafloor to deal with. But for our tests, it's clearly a problem how you actually determine that. I mean, you could think of it if you look at the images. This could be seafloor, this could be kind of iceberg, but it's a thing you want to consider when you do something like that. Here again, on the glider, what we used for mapping, we used the full sector, the scanning sector that we can set, plus minus 45 degrees, for example. But for the navigation, we used only a subset of that. So in our case, we used plus minus 5 degrees, I think, because that was the relevant kind of sector for us. And the behaviors we implemented were search for the iceberg, so you're far away, set a course for the iceberg where you have an initial guess, and then start a search pattern and see if you can detect the iceberg, then follow the iceberg, and then if you lose it, reacquire it. So that's kind of the idea behind that. Just the technicalities of it a little bit. We used occupancy grid map that moved with the glider around, and we updated with the vehicle's motion and motion estimates. And it's updated based on an inverse sonar model. I'm not going into details. There's a sonar equation in there. We accounted for directivity and incident angle, and basically we changed the probability of the occupancy of the cells based on this model, and it worked actually very well for us. We got rid of a lot of noise in the system, and it proved to be pretty robust for us. Based on that, we basically got a shape of the iceberg in the proximity where we wanted to go, and from there we used line of sight trajectory following to get back to in the trajectory and around an iceberg. We tried different kind of complex and very simple kind of approaches to find the shape that we wanted to follow. At the end of the day, the straight line worked the best because the icebergs are so irregular that any polygonal kind of following was, it's the same thing. You don't know what it is, so we had a little horizon looking forward, and it worked very well for us. The heading control, as I said, is line of sight. Here is a simulation. We tested everything in simulation. So the iceberg that you see there is actually from a database that exists, the digital database of icebergs. It's an approximation. And then we implemented the dynamic model of a glider and our model that I showed you about getting the information. You see actually in some of the corners it overshoots, it loses the iceberg, it switches back to the searching and reacquire mode and then drives around it. So that was our simulation. The iceberg at the same time, I should say, is drifting here and rotating a little bit. So that was our simulation environment. From the first field experiments on a grounded iceberg, we got, in the first trial, we got the 75% loop around an iceberg, and then we got 2 loops around it, and next day another one. And from there, you saw some shift in the iceberg, and we associated that a lot with tidal changes. You have a little bit of tide, and so the iceberg, when it sits on the seafloor, it basically rolls a little bit over and does that. So that was quite successful. And here's just some, as I said, the point cloud didn't do it. They needed a little bit more. This still is not the perfect thing they wanted to see, but we got pretty close. So what we detected was the iceberg motion from the tidal effects, and we saw a little bit of the iceberg orientation change also. These are 2 scans, I should say, at different days. Ultimately, in 2017, we had the first full trial, I should say, and here's kind of a summary of that, where I show you here the wind field. So this is from the meteorological station, shows you the iceberg in the middle, and the wind field around the iceberg plotted. We drove several times around the iceberg with a surface vehicle, shows you how it changes a little bit from between 0 and 2 meters per second. Over here is a temperature field, and what you expect, the wind is blowing in this direction, you get in that direction also the meltwater from your iceberg. So you will see that, and that's also produced here in the salinity. Meltwater you associate with fresh water, so you get a fresher kind of plume here. You have some other spikes here. There might be a current, which is actually shown here, but we didn't have a wide field to say what the global current is around the iceberg. This is the local current around the iceberg. And so this showed a very consistent kind of data set. And the people we showed it to and worked with, they were extremely happy with it because it all made sense to them how their understanding was of the icebergs. From the mapping side, we mapped the iceberg, and we fused it together with a LiDAR. And in this case here, you see what I referred to earlier, what's seafloor, what's iceberg. You see there, and there's still some artifacts left in there, but in general, we were able to produce a very nice kind of shape information of this iceberg. And so that was together the USV Sea Dragon with a LiDAR, the multi-beam, and underwater with a scanning sonar, putting that together. So of course, this was not, by far not my work alone. There's a whole slew of students and engineers involved, oceanographers, and Memorial Technical Services were very invested in it, and they did a great job in providing us all the necessary kind of support. And the funding for this project, it was about a $5 million project, was provided by the province, by the federal government, but also by Suncor Energy, which was our commercial partner. They didn't provide a lot. There's a little anecdote maybe to say there is that we had also another offshore partner that were ready to invest in it, and then they changed their local manager around, and he came and said, this is science fiction. I think in the beginning, yesterday in the section, somebody said, this is science fiction, but we showed them that we actually can do it, and they came 2 years later and said, oh, you should do this, because they had changed the manager again, right? So said, yes, well, we did. So with that, I want to conclude, and here is just a project that we started last year, and Arne, where's Arne? Here's Arne. We'll be able to tell you a little bit more about it. It's a vehicle that's much smaller. It's only 1.5 meters long, supposed to be, and it's supposed to explore the seafloor in very close proximity without disturbing it. So this is something where we're trying not to do a hovering vehicle to impinge on sediment, and we try to use deformable actuators, a couple of new technologies to evaluate them also for Marum has a large operational marine technology side, so we are seeing ourselves as, being on the bleeding edge, as we say, and tell them this works and this does not work. So we're very excited about that. So hopefully the next BTS if you don't bring it, we'll tell you more about it. So thank you very much.